The next part of this lecture is about sample collection. Our learning objectives for this part of the lecture is to determine appropriate locations and types of samples to collect, to calculate volumes of aliquots for a flow proportional composite sample, and to apply statistical power analysis to determine the appropriate number of samples to collect. So let's say we are conducting a study of water quality. We want to determine our sampling locations for a study of pollution. Let's say that pollution coming from a wastewater treatment plant. So some potential sample locations that we might select would be the influent and the effluent of the treatment plant. Perhaps we want to know how well is that treatment plant performing at reducing the pollution. We might also look to collect samples upstream and downstream of the effluent discharge location to see how much the effluent is changing the concentration of that constituent in the water body. And then we might collect samples at locations further downstream from the discharge point to see if we continue to detect the constituent at similar levels to what we detected downstream, or if perhaps it decays quickly as it flows down the water body. So if we're looking at the treatment plant, there are different types of sampling locations that we might choose, and it all depends on what is the objective of our study. So if our objective is to evaluate the final quality of the effluent and maybe compare it to some compliance threshold, then this would be this first example. No matter how many unit processes we might have in the treatment plant, we might only be interested in collecting the sample at the final effluent. If our objective is to evaluate the performance of the treatment plant as a whole, then we might also collect an influent sample and then compare the two concentrations. However, if our objective is to evaluate the performance of each of these individual unit processes in series, then we would collect samples in between each unit process as well. In terms of the holding times and what containers we need to collect the samples in, this information is typically included in a table in the quality assurance project plan, but this is an example of what you might have. So you'd have the parameter that's going to be measured. You would want to include some reference to the method number, the standard method that's used. So maybe it's from the EPA standard methods, or maybe it's some other type of method that's been standardized by a different organization. You might specify something like the maximum holding time for the sample, what containers the samples will be collected in, and if there's any methods that are going to be used to preserve those samples, like keeping them cold or adding some type of acid. So we have different types of environmental samples. The first type is a grab sample, which is measuring the instantaneous conditions at that moment in time that you collect the sample. It doesn't guarantee you that that's the representation of how the concentrations are throughout the day. However, a grab sample is the easiest type of sample to collect because it's just a single moment. The composite sample is going to give a better approximation of average conditions over the course of time. So this could be, there's two different types of ways to collect a composite sample. Let's say if you have a river, you could have a fixed volume composite sample where you're collecting the same volume every single hour, let's say, and then at the end of the 24-hour period, if it's a 24-hour composite, you're mixing all of those individual volumes together into a single sample. You could also collect flow proportional volume samples, which are composite. So if the flow rate is greater, you would collect a greater volume at that given time. And then if the flow rate is lower, later on, you would collect a smaller proportion in order to get a more representative sample of the flow coming through the system. If you're interested in getting concentration profiles over time, you might look instead at collecting a sequence of grab samples. So if, let's say, throughout the course of a storm event, during a rain event, you want to understand what is the level of solids concentrations in a river. So In that case, you might take a sequence of grab samples throughout the storm, or maybe you install a sensor that can detect that parameter, whatever parameter you're interested in, detect it online, and therefore get a semi-continuous measurement. Here's an example problem to calculate aliquot volumes for temporal composite samples. So develop a plan to collect a 1 liter fixed volume temporal composite sample, and for part B, to collect a 1 liter flow proportional composite sample of wastewater at a treatment plant. The flow rate is shown below for different times of the day. So this example can be found in your assigned reading and can be completed using Excel spreadsheets that are provided along with that reading. Here's the solution. For a fixed volume sample, let's suppose that you choose to collect a fixed volume composite sample of 1 liter, and you've got the following times of the day. Since a fixed volume sample is just the same volume at every interval, you'll just collect 125 milliliters each time every 3 hours. That's a total of 8 subsamples. So if you divide 1,000 divided by 8, you get 125. So by collecting these subsamples, once you mix them all together, it's going to give you a total volume of 1 liter. For the flow proportional composite sample, you will need to use the following approach. First, you have to assume what the average daily flow rate is probably going to be. And sometimes you would take that assumption and then use a value that's a little bit higher just to make sure that you indeed get enough volume for your sample. Then you would divide the desired sample volume by the number of subsamples to get the subsample volume as if it were a fixed volume composite sample. While you're sampling, you will measure the flow rate each time a subsample is collected and calculate a multiplier ratio by dividing the measured flow rate at that instant by half of the assumed average daily flow rate. And then we're going to use that multiplier ratio to multiply it by the average subsample volume to get our sample volume at each time point. So the example calculation here, we've got the first aliquot. Let's say the flow rate is measured to be 1.2, like we have in our example. The ratio of that flow rate to the average flow rate, 1.2 divided by 2.9, that ratio is 0.416. So if we take 0.416 times 83.3, where 83.3 is the 1 liter divided by 12 aliquots, then we will get the value of 35 milliliters, and that's the volume of sample that we need to collect at that first time point. We would do the same calculation for each subsequent time point, measure the flow rate, and then calculate how much volume needs to be collected. If you do this calculation correctly, you will see that the sum of all these volumes will add up to your total volume desired of 1 liter. The next question we need to answer is how many samples do we need to collect? So in order to conduct experiments that are scientifically sound and also make the best use of limited time and funding, we need to use something called a power calculation to determine the appropriate sample size. And when I say sample size here, I mean the statistical sample size, not the environmental sample volume. Power calculations start by defining your level of acceptable error. So we typically use 0.05 for the alpha error and 0.2 for the beta error, which is the same thing as using 80% statistical power. The next thing we need to do is define the desired standardized effect size. This is also known as Cohen's d. So what this means is this is the difference that you desire to detect, the difference that you want to detect in your sample, and divide that by the standard deviation of our sample mean. Let's do an example because it'll be easier to understand, I think, with an applied situation. So let's suppose that we're trying to determine if a groundwater source has an average nitrate concentration that's significantly greater than 10 milligrams per liter. Our standard deviation on past measurements, let's say we know from past studies that when we measure nitrate in these types of systems, our standard deviation usually comes out to 2.4. So if the true concentration, which we don't know before we collect the sample, but if the true concentration is actually, let's say, 10.0001 milligrams per liter, that's a very, very small difference above our threshold of 10. So we would really never be able to detect significant results at that level unless we had a very, very large sample size. But if we have a difference that's a little bit more modest, like let's say we want to be able to detect a significant difference if the true concentration is actually 11 milligrams per liter, that's 1 milligram per liter above our threshold, we would probably get a much more reasonable sample size. So let's try to figure out what that would be. So if our threshold of what we want to detect is at least 1 milligram per liter greater than 10, what is the Cohen's d value? How do we find that? All right, so let's use a statistical analogy for how to understand hypothesis testing and the results of a statistical test. So in our engineering situation here, shown in the white text, let's suppose we're trying to see if the nitrate concentration is significantly greater than the regulatory limit of 10 milligrams per liter. The analogy in a court setting is shown here in the yellow text. So in a court, we might have a prosecutor who's trying to see if the defendant can be convicted. Let's say the defendant is on trial for exceeding a speed limit while driving, exceeding the speed limit of 100 miles per hour. All right, so if we were to do this test and we get an alpha error, this is the same thing as like being falsely convicted for a crime. So in our engineering case, the alpha error would represent a situation where the nitrate concentration does not actually exceed the limit of 10 milligrams per liter, but just by chance, by random chance, the sample that we collect and we calculate the average of that, it indicates that it significantly exceeded that threshold of 10. The analogy in the court setting would be where the defendant was not actually exceeding the speed limit of 100 miles per hour, but the evidence indicated that they were. So this evidence might be just purely coincidental and misleading in a sense. All right, so this is an error, and this is what we refer to as the alpha error. The situation where we fail to reject the null hypothesis is analogous to a situation in a court where an innocent person walks. All right, so in our engineering case, this is where we have the nitrate concentration does not actually exceed 10 milligrams per liter, and our sample indicates that there's no significant difference. So we fail to reject the null hypothesis. The analogy in the court setting is that the defendant was not actually exceeding the speed limit of 100 miles per hour, and the jury found the defendant to be not guilty. The beta error is where a guilty person walks free. So here in our engineering situation, the nitrate concentration actually does exceed the limit of 10 milligrams per liter, but our sample did not show the difference to be significant. And that might have been because we didn't have enough evidence. The sample size was not large enough. We didn't collect enough samples. And the analogy in the courtroom is that the defendant was actually exceeding the speed limit, but the prosecutor did not have enough evidence to prove it. Finally, the situation that we're usually always desiring to have in a study is what we call statistical power. So this is the analogy of where a guilty person is convicted. So in our engineering situation, this is where the nitrate concentration actually does exceed the limit of 10 milligrams per liter. And we collected enough samples that we found a significant difference, and we're able to prove that indeed the nitrate concentration is above that threshold. The analogy in the courtroom is where you have the defendant exceeding the speed limit, and the prosecutor was able to gather enough evidence to convince the jury to convict that person. So there are the four situations you could have, four different outcomes you could have for a statistical test. So getting back to our question of how many samples do we need to collect? To do that, we need to perform, like I mentioned, a power calculation. Power calculations can be easily performed using some statistical software packages such as R, Minitab, etc. But we can also use some spreadsheets that are associated with your assigned reading. So regardless of whatever package you use, if you use some software package or use the Excel spreadsheet that was provided, in all of those cases, you need to provide the following inputs in order to calculate the required sample size. So let's say we're doing a t-test and we want to know how many samples do we need to collect in order to get a high probability of a significant result in the t-test. We need to know what the Cohen's effect size is. So how big of a difference are we trying to detect? We need to know what the desired alpha error is, and that, like I said, typically is default at 0.05. We need to know what the desired beta or type 2 level error is, and that's typically assumed to be 0.20. We also need to know what type of statistical test. So is it a one sample test, a two sample test, paired, is it unpaired, one-sided or two-sided? This will all be concepts that are further clarified in your reading assignments. And the next thing we need to think about is, do you need to know what type of study you're going to be doing before you can determine the appropriate sample size? So do we need to know if it's a compliance study, or do we need to know if it's a type of study where we are comparing two different processes before we can determine the appropriate sample size? The answer there would be yes. We need to first determine what is our purpose for doing the study. What kind of question are we trying to answer? What statistical test do we need to answer that question? Only then can we use an appropriate power calculation to determine the sample size necessary to adequately answer that question. All right, example 2.3 is to determine the power based on effect size and sample size. And this example can be found in your reading assignment.